Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today we have Heiko Rocklin from Computer Science Department in the University of Aachen from Germany. He'll talk about congestion games optimization in competition.
Okay, thanks, Wahab. Hi. As Wahab said, I'm going to talk about congestion games today, and this talk is mainly based on two papers, which are joint work with Heiner, Ackermann, and Berthold Voecking. And let me start by telling you or by reminding you what congestion games are. And actually, congestion games are a very old and very well-studied model from game theory. And they are used whenever one wants to model some kind of resource sharing or resource allocation among uncoordinated selfish agents. And the classical example is here on the first slide. So here we have a set of drivers, and each driver wants to allocate a set of roads that leads him to his destination as fast as possible. And you can already see one major problem with this approach due to the lack of coordination and the selfishness of the drivers. We do not reach a situation that is in some sense socially optimal, but traffic jams and other bad things can occur. And in recent years, these congestion games have also attracted much attention in the computer science community. I mean, it's probably not hard to imagine that instead of drivers and roads, we have packets that are routed through a network, or we have tasks that are load balanced between different servers and so on. And so there are lots of applications in computer science, and formally a congestion game consists of a set of players, and I will assume that we have n players in the following. Then we have a set of resources, let's say we have m resources, and in fact in most computer science applications you can think of these resources as the edges of a graph. And now players compete for these resources. So every player wants to allocate a certain subset of the resources. And players cannot allocate arbitrary subsets, but they are restricted. So every player has a set of strategies, which is basically just an arbitrary set of subsets of the resources. And in this example, where the resources are edges of a graph, we could associate with each player a source node and a target node in the graph. And we could, for instance, say that player I is only allowed to allocate subsets of resources that correspond to paths from a source to its target node. And these are the first three components. And to make this interesting, we introduced the fourth component, which are delay functions. So for every resource, we have a function that basically just maps the number of players on that resource to the delay that they incur. So for instance, this edge here, it has a delay of 2 if it's used by one player, and it has a delay of 6 if it's used by 2 players. And now every player is interested in minimizing his delay. And the delay of a player is, of course, we just look at all resources that he currently allocates, and we sum up their delays. That's the delay of a player, and every player wants to minimize his own delay. And and so from the local point of view of a player, this is just a combinatorial optimization problem. So in this case, every player wants to solve a shortest path problem. But the difference to a usual combinatorial optimization problem is, of course, that the delays are not fixed. So each time one of the players changes his strategy, he might affect all the other players. So from the local point of view of one of the players, this is a combinatorial optimization problem, but the delays change from time to time. And here's a simple example. Here's again the network from the previous slide. And here we have two players, the blue one and the red one. And each of these players wants to allocate a spanning tree on the subset of the vertices. So let's say the blue player wants to allocate a spanning tree on these 3 vertices, and the red player wants to allocate a spanning tree on these 3 vertices. Then first of all, you can notice that the only edge that can be in both spanning trees is this vertical one. And it will have a delay of 1 if it's used by one player, and a delay of 5 if it's used by both players. And let us assume that we start with an arbitrary assignment of strategies to the players. So maybe the blue player starts with this spanning tree, and the red player starts with that spanning tree. And observe that in this situation, none of the players is happy. So both of them currently have a delay of 7, but both of them could improve their delay by allocating the vertical edge and deallocating one of their other edges instead. And so maybe the red player does so. So then he has a delay of 4, and that's the optimal delay he can achieve given the fixed strategy of the blue player. And now you can see that the blue player can still improve. So he still has a delay of 7, but even if he switches to the vertical edge, it will have a delay of 5, which is still better than 6. So also the blue player changes his strategy, and now you see the whole problem with this approach. The red player has become unhappy again. And in this simple example, it suffices for the red player to make one more move. So the red player can change his strategy once more, and now we have reached a situation in which none of the players can decrease his delay given the fixed strategy of the other player. And such a state is of course called a pure Nash equilibrium. And a state in which none of the players can unilaterally decrease his delay. And in this talk, in the following, I will only be concerned with pure Nash equilibria. I mean, you might know all these recent PPAD hardness results. They are with respect to mixed equilibria, where players can have probability distributions over the set of strategies. But somehow, I think that pure equilibria are in many games more natural, and they have the advantage, or one advantage of the mixed equilibria is usually that they always exist. Pure equilibria do not always exist. But in a minute we will see that in congestion games we have always pure equilibria. So it makes sense to restrict one's attention to pure equilibria in such congestion games. Okay, and the remainder of my talk basically consists of 3 main parts. In the first part, I will be concerned with the uncoordinated behavior of the agents. So what happens if agents, one after another, iteratively improve their strategies? Do they reach a Nash equilibrium, and if so, how long does it take? And the second part is about the complexity of computing equilibria. So if you have some kind of central coordination or central authority, then it might be an interesting question whether you can actually compute equilibria efficiently or not. And okay, last part is about extensions of the model to weighted players and player-specific delay functions. But let me start with the first part. Let me start with the uncoordinated behavior. So what happens if agents, one after another, iteratively improve their strategies? And the first result I have to mention here is due to Robert Rosenthal. And he showed a couple of years ago that every congestion game admits an exact potential function. So what does that mean? Basically, it means there's a function phi, which maps the current state of the game to a natural number. Okay, it has the additional property that this potential is always bounded from below by 0 and bounded from above by n times m times dmax, where dmax shall denote the largest delay value that occurs, that is taken by any of the resources. And the important property is the second one here. So each time when a player decreases his delay by some given value x, then also the potential function decreases by exactly x. So it decreases by exactly the same amount. And these two properties together, of course, imply the following. Every sequence of beta responses, so every sequence in which the players, one after another, iteratively improve their strategies, terminates after a pseudo-polynomial number, so after n times m times dmax, many steps. And so in particular,
what is m in this case?
Oh, m is the number of resources, and n is the number of players. And okay, so we know that if players iteratively play best responses, they reach a Nash equilibrium, or they reach a state in which none of the players can further decrease this delay. And so in particular, a Nash equilibrium exists. Okay, that's a very nice result. And yeah?
What is pseudo-polynomial?
Oh, pseudo-polynomial, I just wanted to indicate that the number of steps depends polynomially on the input size, on the number of players and number of resources, and also polynomially on the largest number that occurs in the input, so on the maximal delay that occurs. Okay, and actually this potential function is not very complicated. It looks as follows. So for a given state S, we denote by nr the number of players that currently use resource r. So the number of players I with r is in Si. And then, in order to get the potential value, we just sum up over all resources. And for fixed resource r, we sum up the first nr delay values. So here's an example. Here's again the example from one of the previous slides. And here you can see we have a potential of 10. Since we sum up 1, this edge is used by 1 player, and this edge is used by 2 players. So we sum up 1 plus 5, and additionally plus 3. So we get a potential of 10 in this configuration. And if now the red player changes his strategy, then you see the potential decrease from 10 to 9, since now we sum up only 1 plus 1 plus 4 plus 3. And so the player decreased his delay by 1 from 8 to 7 in this example, and the potential also decreased by 1. And as I said before, that's not a coincidence, that's always the case. And it's quite easy to see, since you just need to consider which terms vanished in the sum and which terms appeared in the sum.
In this case, there are actually two pure Nash equilibria, right? If player red chooses the middle one, or the player blue chooses the middle one. But in the other case, the potential function will be different.
Yeah, okay, that's right. It's not the case that every Nash equilibrium has the same potential value. That's true. But I think in this case, I don't know, there's only one equilibrium. I mean, if the red player allocates the vertical edge, then the blue player will still have an incentive to go to this vertical edge. Since if the red player allocates it and the blue player sees, the blue player will have a delay of 5 on that, which is still better than 6. So I think this is actually the only equilibrium in this simple example. Okay, and now why is this an exact potential function? Yeah, as I said, we just need to consider which terms vanished in the sum and which terms appeared in the sum. And if you look at this, the term 5 vanished. And this is exactly the delay of the resource that the red player left. And additionally, we have now a delay of 4, which is the delay of the resource that the player now allocates. And this holds in general. So if a player leaves several resources, then all these delay values vanish in the sum, and the delays of the newly allocated resources appear. So the change in the potential function is exactly the change of the delay of the corresponding player. And yeah, okay, now we have this potential function, and we know that every sequence of beta responses terminates in a Nash equilibrium. And so from a game theoretic point of view, we are now basically done. So we know everything we want to know. But as computer scientists, we are also interested in efficiency. And so the question is, how long does it take until a Nash equilibrium is reached? And as I said, we have this upper bound of n times m times d max. But this is, first of all, only an upper bound. So the question is this upper bound tight, or can we maybe prove something better? And first result here is negative. This upper bound is really tight. So Fabrikant, Papadimitriou, and Tolva proved that for network congestion games, these are games where every player wants to have a path between a source and a target node. In such games, there exist such games with corresponding initial states such that every sequence of beta responses has exponential length. So no matter in which order the agents improve and no matter which improvements they do, they will always need an exponential number of steps to reach a pure Nash equilibrium.
Exponential in both?
Exponential in the number of players. And on the other hand, there is a positive result for very simple games, for singleton games. So singleton games are games where at each time every player allocates at most one resource. So basically you can think that every player has one task and you want to allocate this task to one server. That's a singleton game. And if you have this simple structure, then every sequence of best responses terminates after at most n squared times m many improvements. And so, yeah. We have now a negative result, we have a positive result, and we were interested in the question, how does the combinatorial structure affect this, the convergence time? Or can we, as you see, the combinatorial structure here is very simple. So the strategy sets consist just, or are just singleton sets, whereas here the combinatorial structure is a bit more complicated. Here the feasible strategies are paths. And we were interested in the question, can we in some sense find a characterization which combinatorial structure leads to fast convergence and which does not? And we found such a characterization, and let me first of all give you the positive result. The positive result is, assume every player wants to allocate a basis of a matroid over the resources. Or if you don't like matroids so much, think about spanning trees. Every player wants to allocate a spanning tree on the subset of the vertices. Then every sequence of best responses terminates after at most n squared times m times rank of the matroid many steps. Or for spanning trees, n times m, n squared times m times number of vertices in the graph. Yeah. So for this combinatorial structure of matroids, we have polynomial convergence. And before I prove this, I would like to prove this result for singleton games, since this is quite easy and it's a very nice proof. Okay, why should, in singleton games, the best response dynamics converge in polynomial time? Here is such a singleton game. Let's say every player controls one of these balls, and he wants to place it in one of the bins. And now, when has the blue ball an incentive to change his strategy? Therefore, he looks at an inequality of this kind. He just needs to compare his current delay on resource R with the delay that he will see on R prime. If and only if this inequality is satisfied, he has an incentive to change his strategy. And OK, that's a singleton game. And now the question is, why does it converge quickly? The idea is very simple. We want to reduce the delays without affecting the game. So what does that mean? So we have this pseudo-polynomial upper bound of n times m times d max. But unfortunately, we cannot say anything about d max. Even in a singleton game, the largest delay value can be arbitrarily large, basically. I mean, in this case, the largest delay value that occurs is 150, but there's no polynomial bound on that. It can be arbitrarily large. But the idea is to reduce the delays without affecting the dynamics. And basically, this means the following. We want to find a set of equivalent delays d bar. And these delays shall have the following properties. First of all, they should be polynomially bounded. So d bar should be at most number of resources times number of players. And such an inequality here should be satisfied with respect to d if and only if it is satisfied with respect to d bar. And as I said, if a player wants to know whether he should change his strategy or not, he just looks at an inequality of this kind. And this inequality is satisfied with respect to d if and only if it's satisfied with respect to d bar. So we can replace the delays d by the delays d bar without affecting the better or the best response dynamics. So the game basically remains the same. And this proves already polynomial convergence, since the delays d bar are bounded polynomially. So with this bound of n times m times d max, we get now a bound of n squared times m squared. And in fact, you can get rid of one of the m's if you look more closely. But I think that's not so important here. The important point is really, to find such a set of equivalent delays. And that's actually not very complicated. So all we must do is we look at all delays of all resources. And basically, we sort them. And we look at the smallest delay value, which is in this case 1. And we replace it by 1. OK, that's not very interesting. Then we look at the second smallest delay value. In this case, it's 2. Replace it by 2. That's also not very interesting. But the third smallest delay value in this case is 5. And I claim we can replace it by 3 without affecting these inequalities, since 3 is still larger than 1 and 2, and it's still smaller than any other delay value. So we can replace the third smallest delay value by 3. And we simply continue like that. We look at the fourth smallest delay value, which is in this case 10, and replace it by 4. We replace 15 by 5, and so on. And by this, we really get the set of equivalent delays, since, as I argued, these inequalities stay satisfied with respect to d bar. And we have m resources. Each of these resources has at most n delay values. So the delays d bar will be bounded by n times m. So we've exactly what we wanted to achieve. And this proves polynomial convergence for singleton games. And one remark, why does this only work for singleton games and not for more general games? The reason is simple. If we have, for instance, a network congestion game and we want to decide whether to route traffic across this upper path or across this lower path, then such an inequality is relevant. So we need to compare sums of delay values and not only delay values by themselves. And these sums are not preserved by this reduction of delays. So we only preserve inequalities of this kind and not such more complicated inequalities. And that's why our approach, or not our approach, the approach by Young et al. Works only for singleton congestion games. But
it doesn't also work for if you need 2 resources or a small number of resources. Just extend it of this way, I guess.
You mean if you only exchange 2 resources at each time?
If you need 2 resources the most, then you can just repeat the same proof.
It will be a cardinality metric. So you're going to.
OK, so maybe let's have a look at the next slide. Since I wasn't right that this works only for singleton games. It works for a larger class of games. Namely, it works for all Matroid games. So that's the positive result for Matroid games. And it works exactly as for singleton games, since the we do the same reduction of delays from d to d bar. And now, why should this work for general matroids? Or, as I said, if you don't like matroids, think about spanning trees. And matroids or spanning trees have the following property. Let's say we are given an arbitrary instance, an arbitrary graph with weighted edges, and we are given an arbitrary spanning tree, T0, and an arbitrary optimal minimum spanning tree, T-opt. Then we can always find a sequence of spanning trees starting with T0 and ending with T-opt that has the following two properties. If we look at the weights of the spanning trees in the sequence, then the weights are non-increasing. So they only strictly decrease or stay the same. And additionally, if you compare two neighboring spanning trees in the sequence, they differ in exactly one edge. So Ti contains one edge not contained in Ti minus 1 and vice versa. So here's an example. Here on the left side is an arbitrary spanning tree, and here on the right side is an optimal minimum spanning tree. And you see they differ in a lot of edges, but we can give such a sequence since we start by exchanging this 4 edge by this 2 edge. Then next step is to exchange 5 by 3. And then finally, we have to exchange this 3 edge by that one. And so we have a sequence of spanning trees that differ in exactly one edge and whose weights are non-increasing. So exactly what we wanted to have. And this works for all matroids, and I claim this already proves that also matroid congestion games converge quickly. And the reason is, yeah, as I said, we do the same reduction of delays as we did for singleton games. And if we now look at such a sequence and we look at going from that spanning tree to that one, then you will notice that exactly an inequality of this kind is interesting here, since we exchange one resource by one other resource. And we know that this inequality is preserved. So if we now don't look at this from the point of view of d, but we look at these reduced delays d bar, then also with respect to d bar, this will be improvements. The first two steps will be strict improvements, and the last step will not change the delay with respect to d bar. And so if we play a best response with respect to the original delays, we get a better response with respect to these delays d bar. And so the same arguments apply as before. So we now look at the game with the delays d bar, and we know these delays are polynomially bounded, so we have polynomial convergence to a Nash equilibrium. Okay, so yeah, this was already our positive result, and I promised some kind of characterization which combinatorial structure leads to polynomial convergence and which does not. And here is our negative result. So assume you are given an arbitrary non-matroid antichain. So R is a set of resources, I is a set of subsets of the resources, and antichain simply means there are no two sets A and B contained in I such that A is a proper subset of B or vice versa. But this is just a technical thing. Just think that we are given an arbitrary non-matroid optimization problem, an arbitrary non-matroid instance of an optimization problem. Then for every n, we can construct a congestion game with n players such that the strategy space of every player is isomorphic to this given non-matroid optimization problem. The delay functions are non-negative and non-decreasing, and there is a best response sequence of exponential length. So with other words, for every non-matroid instance of an optimization problem, we can construct a congestion game in which every player wants to optimize exactly this non-matroid instance and which has an exponentially long best response sequence. And so this shows, if you don't take into account further properties of this game, as for instance, like how the strategy space of different players are interweaved or so. If you don't take into account such further properties, then the matroid property is really the maximal property that can guarantee polynomial convergence. Yeah, since for every other structure, we can construct this example with exponential convergence or with a sequence of exponentially many best responses. And let me say one word how we proved this result.
Can you give us like a little longer? So what you said is for any other instance, somehow you can extract out. So you said for any other instance, as long as they don't satisfy the matroid property, they
set structure doesn't satisfy matroid property, and they will write the delay functions for that instance. It's not for any set structure and any delay function. So for any set structure.
So for any non-matroid set system, we can construct this example where every player wants to optimize exactly this non-matrix set system, and we choose the delay values of the resources. Yeah.
Right. Sorry, can you just remind me what sigma I is?
Sigma I is the strategy space of sigma I. So this is exactly the
allowed things that
and
you're saying, and each one is isomorphic to I.
Right. Yeah. Okay, and we prove this result in the following way. So remember, for the positive results of matroids, the interesting thing was that every best response can be decomposed into one-to-one exchanges. So every best response can be decomposed into a sequence of exchanges of single resources. And exactly this property is lost when you go beyond matroids. Since for every non-matroid set system, you can identify 3 resources, A, B, and C, and fix delays of the other resources such that the following property is satisfied. Whenever the delay on resource A is smaller than the delay on resource B plus the delay on resource C, then every optimal solution contains A, but it does not contain B and C. And if this inequality is the other way around, then every optimal solution contains B and C, but it does not contain A. And what does this mean? So think we have one player who is currently allocating resource A. And we are in this setting here. So yeah, he plays an optimal strategy and he allocates A. And now another player also comes to A. And suddenly the delay on A increases, and we get to the second case. And now the first player who in the first place allocated A does not have an optimal strategy anymore. He has to change his strategy. And therefore, he has to deallocate A and allocate B and C instead. So in some sense, we can force this player to exchange one resource, namely A, by 2 other resources, namely B and C. And this is a step which cannot be decomposed into such a one-to-one exchange as for matroids. And for every non-matroid set system, we can enforce a situation like that. So we can enforce such a 1-2 exchange. And this observation already suffices to prove exponential convergence. So I don't want to give you the details of the construction, but the idea is basically we construct an instance with, let's say, n gadgets, and each of these gadgets represents 1 bit of a binary counter. And we initialize this binary counter with all bits set to 0, and then this counter counts from 0 to 2 to the n minus 1. Yeah? And that's not too complicated. Once you have observed this property, then you can come up with this negative example. Okay. This was actually everything which I wanted to say about the uncoordinated behavior or the convergence time. Let me now come to the second part of this talk, which is about the complexity of computing equilibria. And as I said in the beginning, if you have some central authority, some central control, then it might be an interesting question whether you can compute equilibria efficiently. And if you know these recent PPAD hardness results for normal form games, then the story here for congestion games is a bit different. Since, first of all, there are no normal form games, but more importantly, we are interested here in pure equilibria instead of mixed ones. And so the problem of computing equilibria here is not in this class PPAD, or it's at least not known to be in PPAD, but it's contained in a different class, which is called PLS. And before I come to the connection with congestion games, let me first of all tell you a bit about this complexity class PLS. And actually, it has been invented for local search problems. And a local search problem is simply characterized by its set of instances. And for each instance, we have a set of feasible solutions. We have an objective function. And for each solution, we are given a neighborhood, which is basically just a set of feasible solutions. And now we are interested in finding a locally optimal solution. So we are interested in finding a solution in whose neighborhood there's no other solution with a better objective value. That's a local search problem. And we say that it belongs to PLS. If PLS stands for polynomial local search, if there is a polynomial time algorithm for finding an initial feasible solution given an instance, if there is a polynomial time algorithm for evaluating the objective function, and if there is a polynomial time algorithm for deciding whether a given solution is locally optimal, and if not, then this algorithm has to find a better solution in the neighborhood in polynomial time. And if these 3 requirements are met, if we have these 3 polynomial time algorithms, then the problem belongs to PLS. And this is, in fact, a very broad class of local search problems. So most natural local search problems really fall into this class. And yeah, now we have a complexity class. Now the next thing is we can define a reduction concept. And what's a PLS reduction? Assume we have two problems, pi1 and pi2, both being in PLS. Then we say that we can reduce pi1 to pi2 if we have two polynomial time computable functions f and g with the following properties. F maps instances of pi1 to instances of pi2. And g maps solutions for pi2 to solutions for pi1. And the intuition behind this should be as follows. If it's easy to compute locally optimal solutions for pi2, then it should also be easy for pi1. And why should this be the case? OK, assume we are given an instance for pi1. Then first of all, we plug this instance into f, and we get an instance for pi2. And then we solve this instance. So we find a locally optimal solution for this instance of pi2. And then we plug this solution into G. And what we get is a solution for pi1. And we should have the property that whenever we plug a locally optimal solution into G, then we also get out a locally optimal solution. And yeah, if we have these two polynomial time computable functions with this property, then we say that pi1 is PLS reducible to pi2. And as I said, yeah?
Given two locally optimal solutions, if one is, by some objective function, better than the other, does G preserve that?
No, we don't make any assumptions about that. And OK, with this reduction concept, as I said, if it's easy to compute locally optimal solutions for pi2, then it's also easy for pi1. And if it's hard for pi1, then it's also hard for pi2. Yeah, so a very natural reduction concept. And OK, now we have a complexity class. We have a reduction concept. Now the natural question is, are there complete problems? And the answer is yes, there are. And the first PLS complete problem is this so-called circuit flip problem. And this was shown to be PLS complete also by David Johnson, Christos Papadimitriou, and Mihalis Yannakakis. And this problem is actually very simple. We are given a Boolean circuit composed of AND, NOR, and AND, OR, and NOT gates. And the circuit takes m input bits and gives n output bits. And first of all, we interpret the output bits as a binary number. Yeah, so we say that f of these input bits equals the output bits interpreted as binary number. And now we are looking for a locally optimal set of input bits. And we say that two sets of input bits are neighbors if the Hamming distance is 1. So with other words, we are looking for a set of input bits such that the output cannot be improved by flipping one bit from 0 to 1 or vice versa. So that's a locally optimal set of input bits. And yeah, finding such a locally optimal set of input bits was shown to be PLS complete. And that's not trivial, but it's also not too hard to show this. Much more complicated is the following reduction, which was done a couple of years later by Schäfer and Yannakakis. And they showed that it's PLS complete to find a locally optimal cut. So I guess you all know the max cut problem, where we are just given an undirected graph with some weighted edges. And of course, yeah, finding the cut, or finding the cuts, the maximal cut is NP hard, but we can make it a local search problem. We say we want to find a cut whose value cannot be improved by moving one vertex from the right side to the left side or vice versa. And finding such a locally optimal cut is also PLS complete. And this is a really complicated reduction from circuit flip. So I think it takes 25 pages, and it's not very intuitive, this reduction. And OK. That's all I wanted to say about PLS, or maybe one word more. Of course, this would be very boring if PLS would be a subset of P, but that's, of course, not known yet. So, but I think it also wouldn't contradict any standard complexity theoretic assumptions. So it might very well be that PLS is just a subset of P, but we do not know that. OK, but now we have this class. We have complete problems. And now let us come to the connection with congestion games. And first of all, I claim that computing equilibria in a congestion game is in this class PLS. And therefore, we can use as objective function simply Rosenthal's potential function. And we say that a state S prime is in the neighborhood of a state S if S prime is obtained from S by letting one player play a better response. And then a locally optimal solution is exactly a solution in which none of the players can change his strategy and improve the potential value. Or with other words, in which none of the players can decrease his delay. So the locally optimal solutions here are exactly the pure Nash equilibria. And so, yeah, computing equilibria is in PLS, and it's not only in PLS, it's also PLS complete. And this was also shown by Fabrikant, Papadimitri, and Tolva. And again, it was shown for network congestion games. So even if every player just wants to have a path between a source and a target node, it's PLS complete to compute a locally optimal or Nash equilibrium. And here it's important that different players might have different source nodes and different target nodes. If every player had the same source node and every player had the same target node, then the problem was polynomial time solvable, also shown by Fabrikant, Papadimitri, and Tolva. But if you have an asymmetric game, if different players can have different source nodes and different target nodes, then it's PLS complete. And this is, again, a very complicated reduction. In fact, it reworks this complete reduction from max cut, from circuit flip to max cut, and it adds even some further complications. So that's the most complicated reduction I've ever seen. And yeah, again, we have now this negative result for network games, and implicitly we also have some positive results. I mean, for matrix congestion games, a locally on Nash equilibrium can simply be computed by simulating the best response dynamics. So we have some positive results, a negative result, and again the question was, how does the combinatorial structure influence, in this case, the complexity of computing equilibria? And unfortunately, we couldn't find such a nice characterization as for the convergence time, but at least we gained some more insights which substructure really causes the trouble and causes the PLS completeness. And therefore, we first of all defined a very simple class of congestion games, which we called threshold congestion games. And we do not believe that these games are very interesting from an application point of view, but we believe that they are a very good starting point for further PLS reductions. And the combinatorial structure is really simple, since the set of resources decomposed into two subsets, R out and R in. And each player in this game has only two feasible strategies. Each player has its own unique private resource in R out, and he has a subset Si of the resource in R in. And so, for instance, the blue player here can only decide to either allocate its own unique private resource here or to allocate these three resources. These two resources, sorry. And so every player has just one allowed strategies. And we called them threshold congestion games, since in some sense the delay on that resource is the threshold for the player. So if the delay on these resources is smaller than the threshold, then he goes to R in, otherwise he stays at R out. And we can even restrict this further by saying that every resource in R in should be contained in at most exactly two strategy sets of the players. So this here is not quadratic, since this resource is contained only in one strategy space. But even with this further restriction, we could show that it's still PLS complete to compute an equilibrium for such a quadratic threshold congestion game. So here we have a very simple combinatorial structure. Every player basically just can make a 1 to k exchange. So you can exchange one resource by k other resources, where k can be a quite large number. Okay, and how did we show that these quadratic threshold congestion games are PLS complete? And this is a reduction from max cut. So we do not rework the complete reduction here. We just take it for granted that max cut is PLS complete. And given this, we can give a quite simple reduction. So here on the left side, you see an instance to the max cut problem. So basically just a graph with some weighted edges. And we do now the following. So observe that every node here has basically two alternatives. You can decide to be on the left side of the cut, or it can decide to be on the right side of the cut. And so we introduce for every node one player in our threshold congestion game. And this player also has just two possible decisions. Either he can stay on his own unique resource in R out, or it can allocate a certain subset of the resources in R in. And the resources in R in correspond to the edges of the graph. And they have a delay of 0 if they're used alone, and a delay corresponding to the edge weight if they're used by both players. And now a player, let's say the blue one here, can decide to either allocate his own private resource, or he has to allocate all the resources that correspond to his incident edges. So if you look at this blue node here, he has 3 incident edges, and so the blue player has to allocate these 3 resources when he wants to be in R in. And the threshold of a player is set to the sum of the weights of his incident edges divided by 2. And that's the complete reduction, and now I just need to convince you that it works. And therefore, first of all, let me tell you how the function g looks like. And remember, g takes a state of the threshold congestion game and maps it to a state of the maxcut instance. And it should have the property that whenever we plug in a Nash equilibrium into G, we get out a locally optimal cut. And G looks as follows. For player I, we just look, is he currently on his resources in Rin? And if and only if this is the case, then we put node I on the left side of the cut. That's how we map states of the congestion game to states of the maxcut instance. And now I just need to tell you why, if you plug in a Nash equilibrium into G, why we then get out a locally optimal cut. And the reason for this is the following. What's the delay of player I when he goes to Rin? So, as I said, if a resource is used by player I alone, it has a delay of 0, so it does not contribute to its delay. But if it's used by 2 players, then the delay corresponds to the edge weight. So with other words, the delay of player I on Rin is the weight of the edges from node I to other nodes on the left side. Or with other words, the delay of player I on Rin is the weight that it would contribute to the cut if it were on the right side. And given this equivalence, we can say the following. We assume that we plug in a Nash equilibrium into G. So we know that node I is on the left side, so player I is on Rin, if and only if the delay on Rin is at most its threshold, is at most Wi over 2. And so with this equivalence here, we can say that node I is on the left side, if and only if its contribution to the cut when it were on the right side is at most Wi over 2. And this implies that the contribution when it were on the left side is at least Wi over 2. And so with other words, a node is on the left side, if and only if its contribution on the left side is at least Wi over 2. And this means if it would switch to the right side, it would have its contribution to the cut would be less. And so, yeah, we are really locally optimal here. No node has an incentive to change its side anymore, given this equivalence. OK. That was the reduction from maxcut to quadratic threshold congestion games. And now I said that we believe that they are a very good starting point for further reductions. And we have several reductions to market sharing games, to overlay network design games, and in particular also to network congestion games. This is, again, a very simple reduction. So here on the left side is our instance of the quadratic threshold congestion game, and we make out of this a network congestion game. And basically, there is more or less a one-to-one correspondence. OK, first of all, we can assume that for every pair of players, there's exactly one resource that they share here. So for instance, if you pick the blue and the green player, they share exactly this one edge here, this resource. And this is no real restriction. We can assume this without loss of generality. And I will assume that in our network congestion game that we construct, we have delay functions on the nodes. So actually, the resources are the edges, and so we have delays on the edges. But we can simulate also delays on the nodes. That's not too hard to simulate. And given these two assumptions, the reduction looks as follows. So the network that we construct is just the lower left part of a grid, so just a triangle. And if you have 4 players, or if you have n players, then we have the starting nodes are on the left side, so in the first row, in the first column. So starting with S1, S2, and so on. And the target nodes are in the last row, also starting with T1, going to T2, and so on. And now, yeah, the second player, for instance, wants to route traffic from this node to that node. And basically, we choose the delays in such a way that there are only 2 reasonable choices for this player. Either it can route its traffic through the network or through the grid, then it must use the row column path. So it must go as far right as possible and then downwards. Or we additionally introduced a direct edge between the source node and the target node. The player can also use this direct edge. And again, the delays are chosen such that this edge can only be used by player 2 and by none of the other players. So you see, basically, each player has just 2 decisions, to either use this direct edge or to route the traffic through the grid by this row column path. And this is nearly a one-to-one correspondence with this threshold congestion game, since this edge here corresponds to the unique private resource in Rout. And if the player routes traffic through the network, then he is on his R-in strategy. And for instance, if we look at player 2 and player 3, if both of them go to R-in, if both of them route their traffic through the network, then there is exactly one node that they share. And this node gets the delay function of the corresponding resource here. And so, yeah, we have a one-to-one correspondence of this quadratic threshold congestion game and this network congestion game. And this in particular shows that that computing equilibria network congestion games is PLS complete for even undirected networks and even for linear delay functions. So this was not known to be from the previous proof. Okay, and that's almost all I wanted to say about the complexity of computing equilibria. Just one more slide. What happens if the players are lazy? So what happens if we are interested in, say, approximate equilibria? And what do I mean by that? I mean that a state is an alpha approximate equilibrium if for every player his current delay is at most alpha times the minimum achievable delay. So if alpha were 1, then this would be a usual Nash equilibrium. So then the delay of every player would be at most the minimum achievable delay given the fixed strategies of the other players. And if alpha gets larger, this is a more relaxed requirement. And you might think that it's easier to compute such approximate equilibria, but unfortunately that's not the case. So a recent result by Alex Kopalik and Berthold Voecking shows that it's still PLS hard to compute an alpha approximate equilibrium. And this is true for every polynomial time computable alpha. So if n is the number of players, it's even PLS hard to compute a 2 to the n approximate equilibrium or something like that. Yeah, so yeah, it's not easier than to compute exact equilibria. And this is again a quite complicated reduction from circuit flip. Okay, well, that's now really all I wanted to say about the complexity of computing equilibria. Now in the final minutes, I would like to give some extensions of the model of congestion games. So far, I assumed that every player has the same impact on the congestion of the resources. But in many practical applications, this is not really satisfied. So there might be some small players with a low impact and some large players with a high impact. So maybe some players want to route just a short amount of traffic and others want to route a large amount of traffic through the network. And then we can associate with each player weight, which is simply a natural number. And then instead of counting the number of players on a particular resource, we sum up the weights of the players that allocate that resource, and that's then the congestion on that resource. And unfortunately, in these extended models, there are not necessarily equilibria. So it's quite easy to come up with weighted congestion games without pure Nash equilibria. But again, for singleton congestion games, the situation is quite good, since it was shown by Even Da et al. That every weighted singleton congestion game possesses an equilibrium, and even more, every weighted singleton congestion game is a potential game. So with other words, players who iteratively play better or best responses reach eventually Nash equilibrium. But unfortunately, it can take a while. So there are examples with exponentially long best response sequences. And given such a weighted congestion game, or even a weighted network congestion game, it was shown to be NP hard to decide whether it possesses an equilibrium or not. And okay, again, we were interested in the impact of combinatorial structure here. And here is our result. So we could extend this positive result for singleton games again to matroid congestion games. And every weighted matroid congestion game possesses an equilibrium. And if players are lazy, and now I mean by lazy, if a player plays the best response, he exchanges the least number of resources possible to obtain a best response. If you have such lazy players, then these games are again potential games, and players reach Nash equilibrium eventually after playing iteratively best responses. And again, in the same sense as for the convergence time, the matroid property is really the only property that can guarantee existence of equilibria. So for every non-matroid set system, we can again come up with an instance where every player wants to optimize this non-matroid instance and which does not possess an equilibrium. So here again, matroids are the answer to which games possess equilibria. And the argument is actually again based on this one-to-one exchange property. Another extension of the model would be player-specific delay functions. So different players might have different perceptions of reality. Or let's say they might be interested in optimizing different criteria. One really wants to minimize the time it takes to route. The other wants to maximize the reliability or whatever. So they really are interested in different criteria, and they they have different opinions about congestions. And so basically this is modeled by saying that every player has for every resource his own delay function. And not as opposed to the standard model where there's one delay function for each resource. And again, unfortunately, in this extended model, Nash equilibria do not necessarily exist. And again, the situation is better for singleton games, since Milchteig showed that every singleton player-specific congestion game possesses a Nash equilibrium. And he also gave implicitly an efficient algorithm for computing this equilibrium. But unfortunately, if players now play best responses, they even might go into a cycle. So these are no potential games anymore. And again, we were interested in the question whether this can be extended. And again, we came to matroid games. Since again, with the one-to-one exchange property, we could show that every matroid player-specific congestion game possesses an equilibrium which can be computed efficiently. And again, the matroid property is really the maximum property for guaranteeing this. Okay, now just some conclusions. What have we seen so far? We analyzed the impact of combinatorial structure on congestion games. And the easiest case were matroids, in which every best response could be decomposed into one-to-one exchanges, into a sequence of swaps of single resources. And in that case, we could see that every sequence of best responses is short, and in this extended model, models equilibria exist. And if we go one step further, if we go beyond matroids, then we can always enforce that a player exchanges one resource by two other resources. And this is enough to come up with examples with exponentially long best response sequences, and it's enough to come up with examples for these extended versions where equilibria do not necessarily exist. And if we even go one step further, then we get to 1K exchanges, where a player is allowed to exchange one resource by K other resources for some larger K. These were exactly the threshold games. And in that case, we could even show PLS completeness. And some open questions. Okay, first of all, our examples are only of that kind that there exists one sequence of exponentially length of best responses. It would also be interesting to see whether this 1-2 exchange property suffices to construct examples where every best response sequence has exponential length. And also an interesting question would be, how large has K to be in order to prove PLS completeness? So far, in our reductions, K has to be in the order of the number of players. But it would be interesting to know whether a constant K suffices. So is it, for example, already PLS complete if a player is just forced to exchange one resource by 3, 4, or 5 other resources? Okay, that's basically all I wanted to say. Thanks for your attention.
I have one question. So for this best exponential long best response path that you said in the one-to exchange with one-to exchange property, does it is it exponential number of rounds of best responses, or it's so you let each player also play exponential number of times?
No, only some players play an exponential number of times. Basically, you can think that we have n players, and let's say the ith player plays 2 to the n times, basically. So there are some players who play only a constant number of times.
So if you let them play in round robin or something,
unfortunately, then our example doesn't work anymore. So if they play in a round robin fashion, then they converge in polynomial time to an equilibrium.
So there are no games for which all, let's say, there is a starting position that
there are also examples of congestion games where every sequence of best responses has exponential length. So in particular, for network congestion games, you can construct such instances. So that is possible, but we do not know if it's possible only based on this 1-2 exchange property.